Thank you so much for having me. My name is Elmer Roderick Nian Bull, and tonight I'll be presenting how the neural programming language can help create human-readable deterministic AI using biomimicry. I have been a software developer for more than 20 years, and as a software developer, what would sometimes keep me up at night are software errors or flaws, also known as bugs, that are uncovered in production. Some bugs are acceptable, especially if they are non-life threatening. Unfortunately, some bugs can be very deadly. One such case that particularly struck with me is the MCAS software failure. In two unfortunate incidents in 2018 and 2019, faulty software acted on invalid data from a faulty sensor reading, causing the software to activate and pull the nose of an aircraft down, resulting in a tug-of-war between the flight crew and the aircraft. The pilots were pulling up while the aircraft was pulling down. It reminded me of similar situations in the past wherein I had to fix critical, however non-life-threatening production issues quickly. If I had access to the code and I was able to change it, I simply made a few adjustments to it, rebuilt the app, and quickly deployed a hotfix so the error could be resolved ASAP. Unfortunately, not everyone knows how to code, because in order to code, one must be able to understand and write using programming languages. This is, I believe, the root problem. As a programmer for 20 years, I've had to learn dozens of languages, which include markup languages, programming languages, database query languages, domain-specific languages, and so on, and it's not easy. Interestingly, there are now thousands of programming languages, and the list keeps on growing. It got me thinking, how do we humans do it? How do we coordinate our daily lives and adapt to ever-changing realities as necessary? What if right behind our very noses hides a programming language that has evolved for millions of years, that has enabled intelligent organisms to survive and adapt? These questions led me to my exploration of key concepts in neuroscience, philosophy, and linguistics, which by their integration led to the development of the neural universal language, whose basic mechanisms, namely primitive elements, means of combination, and means of abstraction are taken from computer science. Then from neuroscience, it uses neurons and axon terminals as its primitive elements. It then uses neural networks, grandmother cells, and reflex arcs as its means of combination. And finally, from philosophy and linguistics, it uses definitions, arguments, minimalist grammar, and dependency grammar as further means of combination. In a popular programming language called C#, we combine primitive types such as symbols, characters, and spaces to form statements, and eventually if and switch conditions that direct execution to expected outputs. On the other hand, in nature, our nervous systems make use of reflex arcs that convert sensory input into motor output. For example, when a stimulus is encountered, the signal from that stimulus will travel up the sensory neuron to the spinal column. There, it will likely pass through a short interneuron before continuing down a motor neuron to the origin of the signal. Then a contraction of the muscles is triggered, moving the bone. In neural, we use reflex arcs to replicate if conditions and switches in C#, which we saw earlier. For example, simulating the stimulus of the sight of Zach at the same time a reaction is anticipated, the interneuron to the left labeled react when funny actor seen is fully excited, as indicated by the 4 green arrows around it, thereby spiking the response neuron labeled increased volume at the top. On the other hand, the interneuron labeled react when sexy actor seen, this one, to the right is not fully excited since the input neuron sexy was not spiked, as indicated by the red arrow there below. In our Hello Worm prototype, we simulated a very small brain containing only 29 neurons for converting sensory input into behavior, enabling the simulation of a simplified worm that follows odor particles to eventually find food while enabling it to turn whenever it encounters walls. This prototype demonstrates efficient human-readable deterministic navigation capabilities without using any C# if conditions and switches, and while using only reflex arcs. So let me show you quickly. Here. This verb here is not using if conditions and switch conditions as traditionally done in C#. It's using this very small neural network, which if we focus on the specific neurons that are firing for example, sector 2, and when an odor is detected in sector 2, these input neurons at the bottom, sector 2 in odor, connect to an interneuron, which then combine and converge, and then further spike the reactions rotate medium clockwise. So directly converting input to output without using any traditional structures. So just natural structures and processes. Yeah. Using neurUL, we were able to translate this C# code that requires effort and time to learn and which varies across different programming languages into this neurUL code, which uses natural, time-proven structures and processes and only really requires common sense. As we can see here, combining the spikes of sector 1 and other neuron stimulates an interneuron, which in turn stimulates the output neurons to rotate counterclockwise and small. And this then invokes the method in C# because at the end of the day, we're still dealing with traditional programming languages, but in this, at the center is biological neural network simulation. If we can use biomimicry to create a language to convert sensory input into behavior in a human-readable deterministic manner, then can all software be written in neurons and terminals, just like our brains? These are the types of questions we're exploring with the neural programming language. Thank you.
I kid you not, Elmer, but I think I have seen a graphic that after the physical AI era, there's about 4 more eras. I forget what all of them are, but one seriously was the cybernetic era. So I think you're actually getting ready for the one after physical AI, which is quite wild. So you've got a very small set of neurons being able to do increasingly smart things without explicit if-thens. What sort of scale have you built this up to? This, by the way, the world's best name for a hello world, hello world. I think that's fantastic. What sort of scale, and then what happens when you go bigger? Where does it explode? Yeah.
This is a question that came up as well in a previous presentation I did, and it's a very valid concern since at the moment we have data centers, we have demand for data centers being pushed to support AGI. And on the other hand, we have very small real estate for our brains. Just myself, a simple person, I just have this space and I'm able to do simple logic, I'm able to understand things. This simulation here runs on a it's HP now from. And when I checked a while ago, I had the task manager on, I think it was using only 11%. Spiking only consumes 11% CPU. And I think this can really be scaled. And in another presentation that I didn't cover here, I will also show that using biomimicry, we can create databases with 0 duplicates. So that's the reason why in this very small space, we're able to store lots of memories because there's a concept in neuroscience called the memory cell, wherein any idea that you have, you just combine it. You just reduce whatever idea that you already have. You don't duplicate. If you check the relation of databases at the moment, you will see thousands, millions of duplicates, depending on that.
Gotcha. So it's not only efficient for potential the logic can be condensed, but also storage can be massively condensed. That 11%, surely half of that is drawing pixels and drawing a screen and wrapping the thing around the thing. What do you envisage as some of the outcomes, and what's the timeline you're working towards? What's the next couple of steps in this kind of field?
Yeah, so just a few weeks ago, which really pushed me to do this. I was planning to do this back in December because I was part of this Biomimicry Institute workshop that looks into how we can use nature as an inspiration for technological solutions. And it was just in my head for a few months. And then just a few weeks ago, they were able to map out the C. elegans sperm, the inspiration of this project. They were able to map all the individual neurons that are firing together that enable it to find food, avoid alcohol, because alcohol is what's used to make it go away.
Okay.
Right? And it only has 302 neurons.
Wow.
302 neurons, and it's able to survive and host a very simple brain. And we have children.
Okay, good. Okay.
So I think it's
So
just
there's a bit more space to go.
yeah, because there's lots of neurons left to go, but I think this is a way that we can create AI that is human-readable. So at least if Terminator comes, we'll be able to understand why.
Nice one. So what's on your roadmap? What this time next year do you hope to be doing? Are you going for scale or interface, or what sort of challenges are you trying to solve next?
My main challenge at the moment is to ensure that this is community-based. The project is community-based. I want to ensure that this is as free as water. And I think that will enable it to evolve naturally, just like our plates.
Nice. So this to be open sourced, shared, and community built around it to actually build more and more blocks.
Yes.
Gotcha. Dom, are you with us? Are you still in the building? Yes, you are. No? All good. There's a Nexo block. There's an awesome machine with an experiment up. Yeah. Question to you then. You've got hard-coded logic with stickers and paint and. Can you see yourself going from hard logic with traceable code to something that is neurons and it's got to figure it out?
In elements, I would say. So we have two main production elements that we have right now, which is a very deterministic robot and then a AI full recognition scanner.
Yeah.
That one, I can see a lot of merit being able to debug through visual, or at least some sort of tool that would be really, really valuable. That being said, it's a huge model. We run the entire thing on a 6 gigabyte on-device GPU. That's going to be a lot more than the 23 neurons on the
Yeah.
if we could, like, the idea of making it community-minded is probably the most exciting thing about this. Making it in the hands of young people, passionate individuals that want to push it to, like, you will be able to make it, if you make a company out of this, you'd be able to have, say, 3 people on board, push it as hard as you can. Open source, free time of people, and trying to push it in the hands of passionate people, is the way to get this done the fastest possible can. I love it.
Awesome. Now some more questions? Yes. Two right.
Understanding is correct or not. When you're talking about neurons, it's like just a wording, not like physical neurons, like our brains, right? And it's just like different processes running at the same time. Then with different parameters and values, it goes to one like ultimate decision making or like next step to come up with a result. Just like when you meet a person, a boy or girl, you collect all the information, their hair, the height, the body shape, and everything. Then you come up the whether you to talk with that person or not. Is it like that?
Right. So behind the scenes, each individual neuron is simulating a physical biological neuron. So if you view the code behind the scenes, we're actually simulating spike thresholds, the voltage required to stimulate another neuron, actually potentials. Here you can see that it's combining neurotransmitters. So plus indicates excitation, a negative symbol indicates inhibition, and this is a strength. Basically what your neurons are doing in the background is that it's combining actually potentials and then stimulates further neurons down the line. So we are actually simulating biological neurons. This is a simulator of biological neurons. Yes. I mean, there are no physical neurons in the background. It's just digital. Electronic, yes.
And like sensors.
Yes. Yeah. Yes. Yeah.
running at the same time.
Definitely. So you can see use cases in maybe drones. So maybe in the future drones can be self-contained and they will require less resources because you will just be using these neurons to process. So our future step would be to create a 3D space instead of a 2D space like what we're using here. So you can see maybe that worm actually going in its environment and trying to find food.
The sci-fi choice is strong, but I surely don't know brains in a jar behind the scenes. Any question in the back? I think from the Xenon team.
No, I've got the answer.
Got the answer?
I don't know what it was.
Open questions for Elmer. Well, yeah, please, far away.
That's a really, really fascinating presentation, and a really good reminder that the challenges and the problems that we face when we start to mature and physical AI make it actually work in the world. Porting across the paradigms, the tools, and the logic that we apply in the software world is just is not going to cut it. You need new ways of thinking and new ways of problem solving, and so it's really great to see foundational research and looking at the biological world. There's so much more to learn. I have to disagree with one thing that you put up there. I fairly believe that Zach is both funny and sexy.
There we go.
And your model needs to account for that.
Well said, Andrew. Well said.
Different wavelengths, yeah.
Final call for questions?
Thank you.
Elmer, thank you so much for that chat.